I built a rocket in my basement. I'm gonna fly it to the moon. This supersonic is amazing. You're gonna feel my sonic boom. I'm flying higher and I'm never coming down. Look at me now. Look at me now.
Okay, we're going to finish up our discussion of operational amplifiers here. The reason that these op-amps are called operational amplifiers has to do with the fact that they can perform mathematical operations like add, subtract, multiply, divide. They can also integrate and differentiate when we add other elements besides just resistors into them. So let me show you that by showing you a couple of mathematical functions that op-amps can do. Let's begin with a summing amplifier. So the output's going to be the sum of the inputs, or it will actually be a scaled sum of the inputs. And it might look like this. All right, so here we've got three input voltages, V sub A, V sub B, and V sub C. Now, we've been talking about DC all throughout the circuit, but these don't have to be a set direct current type of voltage. These could be time-varying voltages. These could be sinusoids, or these could be, say, the output, voltage output from an amplifier of a guitar. So these could be outputs from a microphone. Those could be anything going in here. All right, and when it's passing through these three resistors, R sub A, R sub B, R sub C, you can see we've got one feedback resistor here, and the non-inverting input goes straight to ground here. We'll use the techniques that we've learned already to solve this one, and what you're going to see is that the output is going to be a scaled sum of the input. One of the things you'll notice right away is that that goes straight to ground, and if that goes straight to ground, then that's V sub P, and that V sub P is equal to 0. Okay, and also this is going to be V sub N up here, and V sub N is going to also equal 0. All right, so you notice that those two things right there are both equal to 0 in this case, and you know we have no currents going in. So now that we've got that, we know we've solved for one of these, V sub P in this case, which gives us V sub N, and now we'll use the node voltage method to write equations for the rest of these. And from that, we'll be able to solve the circuit itself. Okay, so I'm looking up here at this node right here. All of this here is the same node. That's one node, and that is the V sub N node. So let's trace these currents back to the reference node through these resistors and through the sources. So let's go along the A side. We're going to have V sub N minus V sub A over R sub A. That's the current that's going through here to here, plus V sub N minus V sub B over R sub B. That's this current, plus V sub N minus V sub C over R sub C. So that takes care of all three of these currents here. We also have a current that's leaving in this direction, and that's going to be V sub N minus V output divided by R sub F, and all of that's equal to 0. Okay, now you know that the V sub N's are all zeros, so those go away, go away, go away. And you can almost immediately jump to the solution here, if you'll see it. Take this V output and put it on the other side of the equal sign, and this becomes V output is equal to, and then multiply by R sub F is equal to all of this right here. So let's bring the minus sign out, and this is going to be V sub A over R sub A plus V sub B over R sub B plus V sub C over R sub C. There. Now I'm going to rewrite this in just a little bit different format. Keep the minus sign outside, and R sub F over R sub A V sub A plus R sub F over R sub B V sub B plus R sub F over R sub C V sub C. There. Now, notice that we've solved for the output in terms of the inputs. And the inputs were V sub A, V sub B, and V sub C. And you'll see that the output is the sum of those, but we've got these coefficients up front that's really a ratio of the resistances, and that's what adds the scale to this. So this is a scaled sum of, the output is a scaled sum of the input. And you see it's inverted, so we've got the negative sign there. Okay, well, what would be an example of something that you could use this for in real life? Well, this could be a sound mixing board. I said you could take say the input of a microphone for this voltage, guitar for this voltage, drums or piano for this voltage. And you want to mix all of those up. Maybe you want to increase the vocals but decrease the piano. Well, by controlling these scaling factors here, you can make the V sub A big or small, and the V sub B big or small, just by changing R sub A, R sub B, and R sub C. And then notice R sub F is everywhere, so if you change R sub F, you're changing everything. So you can think of R sub F as kind of the master volume control, and then R sub A is the resistance that controls the voltage input on A, R sub B on B, and R sub C on C. So this is an example of like a mixing board or a sound board. And each one of these resistances here might be a slider on a sound board. So you could control the master volume by changing R sub F. You can control the individual input volumes by changing R, A, B, and C. Now, if you did something like you set R sub F equal to R sub A, and all of these resistances equal to each other, then it's just a straight sum. Okay, so you can see that. Let's actually do an example then. Triangle's got a little problem there. All right, so this is a summing amplifier. Let's give it some numeric values for our inputs here. And remember, these can change very quickly over time, but let's say for a specific instant in time, V sub A is 1.2 volts, V sub B is negative 1.5 volts, and V sub C is 4 volts. All right, what's the output going to be? Well, based upon our equation, and you could solve this and derive the same equation for this example if you want to, the output is going to be minus R sub F over R sub A V sub A plus R sub F over R sub B V sub B plus R sub F over R sub C V sub C. All right, so that's what the output's going to look like in terms of the inputs. Well, we've got values for R sub F. R sub F is 220K. R sub A, B, and C are 33K, 22K, and 80K, each respectively. And then you've got your inputs for your voltages, V sub A, V sub B, and V sub C. All you have to do is plug those numbers in here. Now let's see, when you do that, let's go ahead and plug those in. R sub F is 220K divided by R sub A, and R sub A is 33K. The ohms are going to cancel, the Ks are going to cancel here, multiplied by 1.2 volts, plus 220K ohm divided by R sub B, which is just 22K ohm, times negative 1.5 volts plus 220K ohm divided by 80 times V sub C of 4 volts. All right, now I'm going to do some calculator magic here. Looks like this is 8 volts. This term here is minus 15 volts, and this term here is 11 volts. If you add all of those together, you end up with negative 4 volts. Let's make sure. Yes, that is correct. All right, now recall that there is a certain range over which an op-amp will behave linearly. And it's going to be based upon these voltages here, the VCCs, or the input voltages. And you can see it's plus 6 and minus 6. So as long as our output is between plus and minus 6 volts, which it is, it's between those two, then it behaves linearly. And we have no problems, okay? So the real output will be negative 4 volts. Now, a good question at this stage might be, well, what happens if you change something? Well, let's play that game. Let's say that we keep V sub A and V sub C, keep these two the same, but we'll change this one right here. We'll make it something else. Or better yet, let's just leave it a variable and say, okay, what kind of values can V sub B take, and we still have a linear output. In other words, we don't saturate. So what values can V sub B take and the output still be between plus and minus 6 volts? Okay, that's the question. All right, so let's play this here. We'll lay this here. The output is going to be, well, let's see, all of these will remain the same. So this is going to be minus 8 volts plus, and this is 220, let's see here, 220K divided by 22K. That's just, what, 10 times V sub B. So this is plus 10 V sub B. Plus, and this last term remains the same, 11 volts. Okay, so this is what our output's going to look like. V sub B is going to vary between some values, and we're trying to figure out what those values are, but we want the output to be in the range of plus and minus 6 volts. In other words, forget about the negative sign out here. What we want is what's in the parentheses there needs to be between, let's say, 6 volts to positive 6 volts. So let's say 8 plus 11, that's 19, plus 10 V sub B. Okay, let's get the negative 19, the 19 volts out of there by subtracting from everything. Negative 19 and negative 6 is going to be negative 25 volts. And that leaves 10 V sub B. And let's see, 6 minus 19 is negative 13 volts. Sure, I'm not checking this. I sure hope I'm doing my arithmetic correctly. Okay, now we need to divide by 10. And V sub B is going to be in the range of negative 2.5 volts to negative 1.3 volts. In other words, as long as V sub B is between these two voltage values, then we will have an output that is calculated by the equation, by this equation right here. Okay, so as long as we've got this configuration here, and as long as V sub B, this one, we left V sub A and V sub C the same, remember, but as long as V sub B is within this range, then our output will be linear. Okay, but let's say V sub B goes over that range, well, or under that range, whatever, and let's, what happens then? Well, if the output, if V output is greater than 6 volts, then V output equals 6 volts. But if V output is less than negative 6 volts, then V output is going to be negative 6 volts. So the answer is always going to be somewhere between plus and minus 6 volts. But if it's in the linear range, we calculate it with the equation. Okay, let's move on and do another type of amplifier here. If there's an inverting amplifier, you expect there to be a non-inverting amplifier. And it would look like this. Okay, now notice we still got a feedback resistor here. However, the V sub G is now going to the non-inverting input. So this is the source. And as soon as we are able to write the output in terms of what the source is, then we've solved the problem. You know that. Okay, well, let's say we use our ideal op-amp constraints, V sub n equals V sub p, and I sub n equals I sub p equals 0. Okay, now if you look at this one right here, you need to be able to figure out what V sub n or V sub p is. This is going to be V sub p, this is going to be V sub n. And V sub p, remember, there are no currents going into the op-amp. So what does that mean? That means there's no current passing through R sub G, so there will not be a voltage drop across R sub G. That means that V sub p is going to equal V sub G. So we can write that down, V sub p equals V sub G. And you just determine that by inspection using the ideal op-amp constraints. Okay, that also means that V sub n is the same. And now we can write a node voltage equation for this top node here. So V sub n minus 0, it's going back to ground here, over R sub s plus V sub n minus V output over R sub f equals 0. And now we can solve for V output. Let's put V output on the other side. And when we do that, this can be written as V output minus V sub n over R sub f is equal to V sub n over R sub s. This pen's kind of weird. Okay, multiply through by R sub f. That goes away, and then add this. And we can write the final answer this way. It's going to be R sub f over R sub s, V sub n plus V sub n. So we could factor out a V sub n. It's going to be 1 plus R sub f over R sub s. All right, so there is our output. Squeeze it in right there. And you notice the output is non-inverting. So there's no negative sign here, so it matches the input. In other words, if this is positive, then this will be positive as well. And this that's in parentheses is the scaling factor. And you can see that if R sub f and R sub s are equal to each other, then this becomes 2. So it has a gain of 2. All right, so that's a non-inverting amplifier. Now these come in various configurations. Let me show you a different kind of non-inverting amplifier. All right, now you notice this is similar but different. Here we have the input coming into the non-inverting side again. And we've added this resistor right here. And this is a variable resistor. That's a resistor with an arrow drawn through it. It represents a variable resistor. How do you figure out V sub p and V sub n in this case? Well, this is going to be V sub p here. This is going to be V sub n up here. But if you notice, it looks a little different than what you're used to seeing. This is not difficult as soon as you recognize what this is. This is a voltage divider. Just like that. And, both sides went to ground, but we could say they're connected at ground. This could be the ground connection there. And this is the 400 millivolts. Here is the 15K ohm. And here is R sub x. And V sub p is coming off right there. So really, V sub p is this voltage between these 2 points right here. So we could even put V sub p right here, like that. So you know what V sub p is once you recognize that, because you can just write the divider equation that V sub p is going to be R sub x over 15K ohm plus R sub x times 400 millivolts. Okay, so you know what V sub P is. Then you know what V sub N is as well then. And we can write a node voltage equation for the top node then, V sub N over 4.5 K plus V sub N minus V output over 63 K equals 0. And putting it on the other side, write it as V output minus V sub N over 63K is equal to V sub N over 4.5K, and we'll multiply through by the 63K, so 63 over 4.5, the K's will cancel, times V sub N plus V sub N is what V output is. Okay, well, V sub N is the 400 millivolts. I'm sorry, oops, said that wrong. V sub N is V sub P right here, so we could write this in terms of V sub P. So it's going to be 63 over 4.5 times R sub x over 15K plus R sub x times 400 milli plus all of that again. All of that again. I don't have room to write it. I'm just going to leave it blank there, but what's in the parentheses there is this stuff right here. Okay, now we have some numbers that we can plug in. We were given numeric values for these. So in this case, I am going to plug in the numeric values and let's see what I get here. I need a value for R sub x in order to make this a little simpler. So I'm going to give myself a value of R sub x equals 60 K ohm. Okay, and whenever I do that, plug it in down here, do the calculation yourself. I believe the answer you get is V output equals 4.8 volts. Okay, now you have to double check and make sure is this saturated or not, and it looks like it's between plus and minus 5, so 4.8 is good. We're good to go, so the value should be 4.8. All right, if we change this value instead, say we made R sub x equals 100K. Okay, well, if you do that, then the output becomes 5.2 volts, and now you're saturated, so the actual output is just going to be 5 volts then. So it's outside the linear range in that case. Okay, so there's another example of a different type of amplifier. That one's called the non-inverting. Let's go on and talk about yet another one. I want you to realize we've been drawing our OpAmps in one way, but it's possible to draw them slightly different ways and there still be the same type of amplifier. Let me show you one. You should be able to recognize that as a certain type of amplifier. What kind is it? What kind have you seen so far? Well, sometimes maybe you need to solve for V output and then just look at it and say, oh, well, that's a summing, that's a non-inverting, that's a something. Let's do that. If you look at this, V sub P is just going to be 20 millivolts. There's no resistor in line here, but even if there was a resistor in line going to the non-inverting input there, it would still be 20 millivolts because there's no current going into the op-amp because of the ideal op-amp constraints. Therefore, V sub P is 20 millivolts. So V sub P is 20 millivolts, and we did that just by inspection. That means that V sub N is going to be the same thing. So when we come down here, we can write a node voltage equation. And you do it exactly the same way. Even though things have drawn slightly different configuration, you do exactly the same steps. This is V sub N. So V sub N over 3K, that's the current going this way. Plus, and now the current going this way is going to be V sub N minus V output over 12K, and that's equal to 0. All right, now, do you recognize it yet? Well, keep going. If you don't, we'll keep going here. You can write this as V output minus V sub N over 12K is equal to V sub N over 3K. This pen is weird. Okay. But anyway, 12K over 3K V sub n plus V sub n is what the output is. Okay, look. What is that? Non-inverting. You've seen this one before. So V sub n is equal to 12K. That's going to be 4 plus 1. So that's going to be 5. V sub n is what the output is. So this amplifier has a gain of 5. And it is just a non-inverting amplifier. Even though it looks a little different than previous versions, it's still non-inverting. So V sub n was same as V sub p, which is 20 millivolts. So 5 times 20 is 100. So V output is 100 millivolts. Is that saturated or not? Well, you weren't given any values here. I didn't give you any values. And if you're not given any values for the supply voltages, then you just have to assume that it's in the linear range. And that's safe. That's a safe assumption as long as unless you are given some voltages so that you can do the comparison. Okay, so that's all of that one. Okay, there is one other type I want to show you, and that's a difference amplifier. A difference amplifier is probably something that you could figure out. It's the output's going to be related to the difference between the two inputs. So this one will look like this. All right, so this one, you see we have two inputs now, V sub A and V sub B. When we're able to write the outputs in terms of the two inputs, then we're done, as you know. So you've seen something like this bottom part right here before. Remember, this is going to be V sub P, here's V sub N, and we should be able to figure out one of those two. Since this one has the feedback on it, we'll want to figure out this one first. So V sub P is another divider equation. So you've seen this before. So V sub P is going to be R sub D over R sub C plus R sub D times V sub B. And once again, we just wrote that divider equation by inspection. We didn't have to do anything other than write the equation down just by looking at the circuit. All right, now that we know what V sub P is, that's what V sub N is going to be also. And we can write the node voltage equation for the V sub N. And there we have that. Now V sub N is going to be the same as V sub P, so I suppose I could just plug it in down here and move forward. But let's solve for V output first. Okay, now we can plug in for V sub N, which is the same as V sub P here. Okay, now we can go through the algebra here, and this will simplify somewhat. If you want to see the steps for the algebra, I believe your textbook goes through these steps. If not, I can show you my notes. I don't want to spend time doing it here. Come to me individually. I'll show you how to do this. But this reduces down using just tricks from algebra to something that looks like this. There. Now you notice we've got scaling factors here in the square brackets. And you can control those by setting the resistances to be whatever you want. But notice here, it is a difference between the two inputs. So your output is a difference between the two inputs. Now, this is the basis for something called a strain gauge. But the basic idea is that, you've got some kind of, let's say a metal bar here. And you place gauges on either side, one there, and these are welded or glued very firmly to the bar here. And you set them up in pairs. They contain a device that has a resistance that changes when it's placed under stress. An example of that might be something like a nichrome wire. If you take a nichrome wire and you stretch it like this, you put it under stress, its resistance changes. And you can also compress it and its resistance changes as well. So if I had a bar like this, and let's say I had nichrome wires in here and a very tiny voltage passing through the nichrome wire so that I could measure its resistance pretty easily, then if this bar starts to bend, like that. Then this top one is going to be just a little bit longer than it was before, and this bottom one's going to be just a little bit shorter than it was before. So I've exaggerated that a lot here. So this one has a lengthened wire, this one has a shortened wire. So the resistances of those two wires right there are going to be different. But if they had exactly the same voltages passing through them, now they have different resistances there. So you're going to have a difference in voltage between these two. You know, by setting these up and carefully monitoring what V sub A and V sub B are, as the resistances through these things change, then you can tell what the strain is on this, or how much it's flexed. And that's like I said, that's the basis of a strain gauge. It's obviously going to be much more complicated than this simple illustration here, but this is an example of a real life thing that involves you know, an operational amplifier. The difference in resistance between these two, remember I've exaggerated these lengthenings and shortenings tremendously. So the resistance change between these two is going to be tiny. So you need to have some way to amplify that difference in voltage there. And operational amplifier is one way to do that. Okay, at this stage, I think we've finished talking about operational amplifiers in general. Let me show you, though, that you can have multiple operational amplifiers, one right after the other. Let's say, for example, you have 2 operational amplifiers in a row. You can have 2 or 3 or ever how many. And let me draw something maybe you haven't seen before this time as well. Okay, here's a problem. I want to know what the output is, but let's take it one step further. Let's say I want to know what that current is right there. Let's call that current I0. So I want to know what V0 is, and I want to know what I0 is. Okay, this is new. There's not a resistor there for the feedback, but it's okay. You'll work it exactly the same way we've done things before. And you'll look here. Let's see on the V sub P. This is going to be V sub P, and this is going to be V sub N. Let's call this output here like V sub A, and then instead of V sub B, this is going to be the output here, so that's V sub A. Well, look here. V sub P is 1.2 volts, and you got that just by observation. And it wouldn't matter if there was a resistor in this line or not, it's still going to be 1.2 volts. Okay, well, what about V sub N? V sub N then is 1.2 volts. But notice V sub N is connected straight up to V sub A. There's no potential difference between those two right there. So what does that mean? V sub A is also 1.2 volts. And you got all of that just by looking at it. Okay, well, if V sub A is 1.2 volts, then that's the 1.2 volts that's going in here. Now you might say, well, why do we even need something like that? I don't know. Maybe you need to isolate these two. There could be some reason. I cannot imagine it off the top of my head, but it's the problem. Let's solve it. Okay, well, what does that mean? That means V sub A is 1.2 volts, and that's what's feeding in here. Now, if you call this V sub P, then this is V sub N for this op-amp. So here, V sub P is 1.2 volts, which means V sub N is also 1.2 volts. And now we can write a node voltage equation for this node. This is all V sub N right here. There's no current going into the op-amp based on ideal op-amp constraints. So V sub N over 50K plus V sub N minus V output over 200K has to equal 0. All right, we can solve for V output out of that. V output then is going to be 200K over 50K V sub N plus V sub N. So what is this? This is a non-inverting amplifier again. Okay, now we're given values for V sub N, which is going to be 1.2. So let's plug in our numbers. So this is going to be 4 times 1.2 plus 1.2. And that turns out to be 6 volts. So we got V output there. Okay, well, what about this I0? Well, I0 is just going to be this current here, and this current here was this one right here. So 1.2 volts divided by 50,000 turns out to be 24 microamps. So that's our I naught right there. There. Okay, there. So if you work a problem like this that has multiple op-amps, that's called a cascade. If you have a cascade of op-amps here, then you work it one at a time. You do the first one, the output of the first one becomes the input for the next one. You solve that one, the output of that one becomes the input for the next one, and so forth and so forth. And then if you want to figure out the total gain, whatever gain is for this one, let's say that's A1, that's the gain for this one. And this one is A2, and then you have another one that's A3, and you want to know the total gain. What's the total gain? Well, it's just A1 times A2 times A3. And that's the way you figure out the total gain for it all. Okay, you may encounter cascade problems in the homework. You may encounter it on an exam sometime in your future. All right, that's it for op-amps. Now, I will warn you, op-amps will continue to pop up throughout the semester, so you haven't seen the last of them.
I built a rocket in my basement. I'm gonna fly it to the moon. This supersonic is amazing. You're gonna feel my sonic boom. I'm flying higher and I'm never coming down. Look at me now. Look at me now. Look at me. We brought the funk into this function. Yeah. We show up dressing to the nines. Okay. Never need an introduction. No matter what, we're feeling fine. I'm flying high and I'm never coming down. Look at me now. Look at me now. Look at me now. Look at me now. I can't stop. I'm never giving up because I'm way too hot to not be at the top. I can't stop. I'm never giving up because I'm way too hot to not be at the top. I'm flying higher and I'm never coming down. Look at me now. Look at me now. Look at me now. Look at me. Ladies, leave your man at home if he don't treat you like a queen. Yeah. Fellas, if you need a role model, then you can roll with me. Oh, I'm flying higher and I'm never coming down. I'm flying higher and I'm never coming down. Look at me now. Look at me now.